Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Buongiorno a tutti. It is my great pleasure to welcome Fabio Cipriani da Milano. And he has a lot of energy, especially when it comes to vector bundles, and he will tell us everything and more about it. So, Fabio, it's all yours. It's our honor and pleasure to have you. Go ahead. It's all yours. Take it away.
Thanks, Piotr. Thanks, all of you. I will report today about a collaboration with Jean-Luc Sauvageot. All of you know very well, concerning a strategy to associate an energy, a number called energy, to vector bundles that will on topological spaces, Riemannian manifolds or other exotic, more or less exotic spaces. And this will be done using some idea of potential theory in the form of energy spaces, so energy functionals. And we will see how an energy functional with the property of a Dirichlet form provide enough calculus, enough tools like derivation and others to compute in principle the K-theory of a space by the algebraic K-theory of a certain algebra that we will see will be called the Dirichlet algebra, an algebra which is associated to an energy on a space which replace the algebra of smooth functions on a manifold. And we will see later, after the definition, the precise definition of the energy of a vector bundle, how this number has some property like subadditivity, is connected to the non-triviality of the bundle in some situation we called low-dimensional situations, low-dimensional settings. And this provides the appearance of special symmetries on this algebra or special projection, which are critical points are just the critical points of the energy, and so that we call them harmonic. And at the end, maybe I will try to suggest some connection with other works of people. Some of the reference are listed here. And to start, we recall some 2 or 3 basic features of classical potential theory, in which one studies the energy of a certain distribution of mass or charge distribution. For example, in 3 dimensions, by the Coulomb law, the energy of the distribution is given by this formula, where the Newtonian kernel appears in the double integral, and this number represents the energy needed to collect, to aggregate, to form this distribution mu, starting from a situation in which the charges are stored in very remote regions, in such very far from one another, in such a way that the Coulomb force between them is vanishing. So this is the meaning of this the energy of a charge distribution. And since the electric field is conservative, we may represented by an electric potential, and the energy of the distribution itself can be written in terms of the potential by an integral with respect to the Riemann, the Lebesgue measure. And so one by this formula here, one is suggested, is forced, is invited to study this functional, the Dirichlet integral, in fact, as a function, as a functional of a function u, which can be always thought as a potential, smooth or not. So study this functional, the Dirichlet integral, on algebras of continuous functions, for example. So with this idea in mind, coming from potential theory, we can consider the following problem. Is it possible to give a measure, to measure how much effort we have to spend to form, to build a non-trivial vector bundle starting from trivial ones. So from vector bundles, which are the product of the base space by a certain vector space. So we will try to give a meaning, to answer this question with a formula.
Sorry, just a very basic question, if I could.
Yes.
So just to ensure myself, the situation is three-dimensional and you have some singularity in this integral, but this singularity is like the first, the power of norm, yes, first power. So in fact, in dimension 3, this is not an essential singularity. These integrals are finite, yes?
This depends upon the distribution. For certain distribution, the energy is finite. There are other distributions, for example, the Dirac measure placed in a point for which the energy is not finite.
Okay,
So
but
this functional can be can attain the value plus infinity. Yes.
okay, but let me. Maybe I'm at this moment only asking about this potential function. So if your measure comes from some density, then this integral is finite. This u mu of x is finite. Yes.
No, can be also plus infinity. Plus infinity.
No, but if the measure mu comes from some density, which is okay, say bounded density.
No, also it comes from a density. Depends on the density.
So I'm a little bit puzzled. I'm asking about the singularity near x in this case. Yes. This expression 1 over modulus of norm, in fact, yes, norm y minus x is singular near x, and I'm asking how the singularity is essential. Maybe I'm thinking about it like a mild singularity, since we are in dimension 3, and here we have first power of the norm. But maybe I'm wrong.
No, in general, the type of singularity which makes the energy finite depends on in the Euclidean case depends on also on the dimension of the space. Yes.
So
Yeah.
Fabio, but I think a simple example is you just take the Lebesgue measure. So mu of the x is just the x, and then is not finite, right?
Yes, exactly. For example.
Yeah,
Is
it's not finite, but yes, but it's not finite due to the how to say it, is not decaying sufficiently fast in infinity, but it is finite near x, yes? Or am I wrong?
No, okay.
Well, no, it's independent of x. So this is a u mu of y. I think there is a typo because you integrate in the x, right?
Yeah.
So the variable is y on the left. And if the measure is a constant one, is Lebesgue, then this is, I mean, when you integrate, you just replace y minus x by x. The integral of 1 over x is whatever is y is divergent.
Yes, but you have taken Lebesgue measure, and Lebesgue measure has infinite support, and therefore this divergence of this integral is due to the behavior in infinity. But I'm asking about the singularity. So in other words, if you take something which is concentrated on some, I don't know, some three-dimensional ball, and some bounded function. Okay, so like uniform distribution of something which is bounded, then this integral would be finite. Yes, I'm asking
No.
basically asking about the simple thing. If you have integral in 3D, then 1 over norm. If you go to polar coordinates, you have Jacobian, which is r squared, and then the singularity is removed. So this is finite. Yes. Sorry for bothering, but okay.
No.
Before we
Maybe
go on, I would like to have some conceptual understanding what is happening, how the singularities could be problematic.
but you see that maybe it's more easier to consider the problem in this representation of the energy, in which to have a finite energy, the potential U has to belong to the first Sobolev space, at least locally. And so even locally, you can have an infinite energy. And it's a problem of the regularity of the potential. If we see the problem in this from this point of view, it's not always finite.
No, I'm not saying that always. I'm saying in the case where the first support of conjunction of two conditions. The support of measure is bounded. Second, this density is also bounded. So like uniform density on some, I don't know, some normalized ball. Therefore, it would be finite. The singularity won't spoil the thing. Okay, but sorry, I'm interrupting too much, maybe.
And so, but the idea was to translate, if you want, this approach, this point of view from classical potential theory in a geometric situation where instead of a distribution of charges, we have a vector bundle, and we want to measure how to give a measure how about the efforts we should spend to form this vector bundle starting from trivial ones. So, I recall just that I will use some tools and language of Dirichlet spaces, which is a kernel-free potential theory. So it's a potential theory which does not need to know the precise formula for the resolvent from the kernel to compute things, to progress. So it's a potential theory which has been introduced by Berling and Denis, and is centered about the idea of energy functionals. So a Dirichlet form or energy functional will be a quadratic form on an L2 space, which will be densely defined and closed, which is real in this sense, and has this contraction property, which is called the Markovianity. This contraction property comes from the characteristic properties of the Dirichlet integral of the classical potential theory. Is verified in particular for the Dirichlet integral on a Euclidean domain. This property, called Markovianity, is equivalent to the fact that the generator associated to the Dirichlet form, so the self-adjoint operator associated to the closed quadratic form, generates a semigroup on L2, which is positivity preserving and contractive on all LP spaces from P equal 1 to P equal infinity. So
what does a wedge 1 on X?
Yes, is the infimum
Infimum, okay.
function A and the constant function 1 on
Okay.
the topological on the space X.
Infimum, okay.
In particular, this Markovian property implies this other property in which the energy of the modulus of a function, a real function, is dominated or is always dominated by the sum of the energy of the positive and negative parts of the function A. In general, this is a consequence of Markovianity, but if the space is compact and the quadratic form vanishes only on constant functions, then it is in fact equivalent to Markovianity, to it.
Sorry, I'm lost in the sentence.
Yes.
Markovianity always implies and it is equivalent to, there is some condition, then implies, and I'm completely lost. If additional X is compact, so what follows from what?
Markovian property is this one, it always implies this other property here.
Okay.
In case the space is compact, so constant functions are in L2, and the quadratic form vanishes only on the constant functions, then the Markovianity is equivalent to this second inequality. In general, the second inequality is equivalent to the positivity preserving property of the corresponding semigroup. But in general, does not imply the contractivity in any space apart from L2. We don't need about this, but Dirichlet forms can be used to construct a Markovian semigroup, and from Markovian semigroup construct Markov processes. So in probability, they are used to as a tool of study and construct many Markov processes on the space X. Already Berling and Denis in their first seminal papers pointed out the fact that the intersection between the domain of the quadratic form and the continuous function is an algebra, is an involutive algebra, which is a form core for the quadratic form. The natural key assumption to develop a rich potential theory is to assume that this algebra, which is always an algebra of any Dirichlet forms, this algebra is uniformly dense in the space of continuous functions. So it's not only a form core in L2, but is also a dense involutive subalgebra of Cx. This regularity property is also central to associate a stochastic process, a good Markov process, to a Dirichlet form. And in one of the papers I showed you at the beginning, we proved that the Dirichlet algebra, when endowed with this natural norm, which is the sum of the uniform norm plus the energy semi-norm, is complete, is involutive, and is semi-simple. In particular, its spectral radius coincide with the uniform norm, so with the norm in the C-star algebra, in the commutative C-star algebra C of X. And so the Gelfand spectrum coincide with X, with its own natural characteristic topology. Also, one can prove that using there exists, for example, finite energy partition of unit, which belongs to B. And so, all in all, one can use this property suggests at least that one can use this algebra as a substitute of the algebra of a smooth function on a manifold or on a Euclidean space. This identity of the spectral radius identity comes from this inequality one can prove on any Dirichlet space by which the energy semi-norm of the product of two functions, A and B, is bounded by the uniform norm of the functions and the semi-norm of the function themselves. Also, in another paper with Jean-Luc, we showed that this concept of energy, the Dirichlet forms, are determined by differential calculus, and in fact they determine a differential calculus on the space X. By differential calculus, we just mean a derivation defined on the Dirichlet algebra B with values in a bimodule, by which we can multiply on the right or on the left the vectors of the bimodules by the functions belonging to the algebra. So also the modulus, the bimodule is symmetric, so there is an antilinear, anti-unitary map J which exchange left and right multiplication and the involution star. And so if one has a closable derivation, then the closure of this quadratic functional, so the square of the norm of the derivative of A, is a Dirichlet forms. Vice versa, any Dirichlet forms can be represented in this way by a suitable and essentially unique derivation delta with a value in some space. For example,
sorry, so what is a differential square root of what in your slide? You have a derivation and you have energy functional, yes? And you are saying that something square root of another thing.
No, differential square root is a way to recall or this formula by which the quadratic form E of A is the square of the norm of delta of A, or this formula by which the self-adjoint operator associated to the quadratic form, to the Dirichlet form, the generator of the semigroup, the generator of the stochastic process, so this generalized always appear as a generalized Laplacian in the sense that L can be is the adjoint map of the derivation we call divergence, composed with the derivation itself. So differential square root can be, it's a short way to recall or this formula or this formula. So it's not a root in the sense of spectral calculus.
So
It's a square root in the sense of Dirac.
okay, so you have an algebra B, yes, you have a Hilbert C of X bimodule H, yes, and then you have an operator L, and you also have an operator D. L acts where?
L acts on the Hilbert space L2. Delta, the derivation, which verify the Leibniz property,
Yes.
goes from the algebra, which is an algebra, a subspace of L2, to the bimodule H, verifying the Leibniz property.
And why
And
this?
so the divergence, the adjoint of the derivation goes from the bimodule H to the space L2. And so this is a generally unbounded self-adjoint operator.
And what is the relation between B and L2 of X? B is somehow an algebra of operators on this L2? I'm lost.
Is this algebra.
Okay. So this
F is
algebra.
the domain of the Dirichlet form, so it's subspace of L2. This
Subspace
is
of, okay, subspace of L2. Okay.
yes. And also one can form by this formula what can be called a Dirac operator, which on a suitable subalgebra of Lipschitz function provides a spectral triple. The main example is, of course, the one of the Dirichlet integral, which is a Dirichlet form on a manifold, on a compact manifold, say, which is defined on the first Sobolev space. So the domain F, in this case, is the first Sobolev space. And by this theory, one can reconstruct from the Dirichlet integral, one can reconstruct the gradient operator. So in this case, the derivation is just reduces to the gradient operator of the manifold. And the gradient operator takes values in the bimodule of square integrable vector fields on the manifold, which can be is a bimodal because we can act on the fields multiplying them by functions, by continuous functions. So this is the main idea, the main example to have in mind. But this theory is flexible enough to deal with generalized Laplacian derivation on, let's say, exotic spaces, which maybe does not support a manifold structure. So it's a calculus which is intrinsic to the energy functional. This theory has been generalized in the non-commutative setting, and today we will just to any for Neumann algebra in a measurable case. But today we will need the extension to the case where the non-commutative space is an honest C-star algebra with unit maybe. And though with a good trace, and on it, the Dirichlet form is a quadratic form on the GN space L2 of A tau, which is real in this sense, and which satisfies, verifies the contraction property called Markovianity. Now the infim, this symbol can be interpreted or by the spectral calculus or in terms of the projection on a suitable closed and convex subspace of L2. So we can study Dirichlet forms also in a non-commutative setting, but today, for the idea, the problem, the geometric problem we have in mind, we consider the elementary C-star algebra with its trace. The L2 space in this case is formed by the Hilbert-Schmidt operator. And our central object will be the algebra of continuous function on the topological compact space X with values in the algebra of compact operators. We denote this algebra in this way. This algebra is naturally normed by this formula. And one recognized that this is the stabilization of the commutative C-star algebra C of X. By this we mean is the tensor product of C of X by the algebra, the elementary algebra of compact operators.
Sorry, Tommy, do you have a question?
Yes.
Okay, can you hear me?
Yes, we can hear you.
Very good. I have a question about this Dirichlet form, which is extended somehow to this stabilization. Is it so that first you have this Dirichlet form on this C of X, and then you are extending in a trivial manner onto this tensor product, or you have some abstract Dirichlet form on this extended space? So I'm lost at this point.
Yes. We will start from a Dirichlet form on the space X or on the continuous functions on it, and we will stabilize this quadratic form in the next slides in a trivial way. You will see, and we will use this tool, the stabilization of the initial Dirichlet form. So we do not introduce any other Dirichlet forms, just the stabilization of the commutative one, in a sense.
Okay, so this
the content of the next slide.
So this small h is a Hilbert space on which any such a derivation acts trivially. Is it so?
No. I indicate by H any separable Hilbert space, and by K of H the algebra of compact operators.
Yes, but I'm asking about the extension of this Dirichlet form from C of X to this stabilization. Is it completely trivial with respect to this added coefficients in K of H?
Yes, but
okay.
Let's go to this formula. No, we stabilize so the Dirichlet forms on L2 of X by this rule. Essentially, if we represent the elements of this tensor product space as matrices, the energy of a matrices of functions is just the sum of all the energy of all coefficients of the matrix. So
can I understand this as a trivial vector bundle, and you are considering L2 functions on the total space of a trivial vector bundle?
But maybe you can see in this way, but for me, this is a way, the most natural way to extend the energy form, the Dirichlet form, from an algebra, in this case, commutative algebra, C of X, to the stabilization of this algebra, so to the tensor product of continuous functions by compact operators. This is the most easy way, and but we will see that.
So this external Hilbert space is not related to sections of some vector bundle over this.
No. It's just
thank you.
It's just an auxiliary Hilbert space. The only property it has to have has to be separable. The only property. This formula for E star, so the extension, the stabilization of the Dirichlet form to C star of X, one can prove that is a Dirichlet form on this non-commutative algebra with respect to this trace, the extension of the trace. And it's a Dirichlet algebra, so the intersection between the C star algebra, C star of X, and the domain of the form, where the energy form is finite, F star. This is closed by under Lipschitz functional calculus. That means that if we take a self-adjoint element in the Dirichlet algebra, and we form a Lipschitz function of it, f of a, then this is still in the Dirichlet algebra, and its norm in the Dirichlet algebra can be bounded by the norm of the original element a times the norm of the Lipschitz function in the Lipschitz algebra on the real line. So essentially the uniform norm plus the Lipschitz constant. And this theorem is not difficult to prove, but the only crucial point, property one use is that when we have a positivity preserving map on a commutative C star algebra, this is automatically completely positive. And so if we associate to the Dirichlet form the generator L, the generalized Laplacian, we can form the positivity preserving semigroup, and this is automatically completely positive. This means that its stabilization is positivity preserving. In fact, it is Markovian on the tensor product of Hilbert spaces. And then
there is another question. Sorry to interrupt, Fabio. Tomek has another question.
Yes.
Yes, I have a question. Could you remind us the general definition of a non-commutative Dirichlet form?
This one. We have a C star algebra A and a trace on it. So we on the space L2. A Dirichlet form is a quadratic form which is closed, real in this sense, and Markovian in this sense.
Okay, thank you. So now this algebra is stabilization.
Yeah.
Now exactly. Now in the rest of the talk, the algebra A is the stabilization of the commutative C star algebra of continuous functions. So it's a tensor product or between P of X and K.
And please remind me, X is compact or locally compact?
Compact.
Compact Hausdorff, okay.
It's compact. And in a previous work, we proved that essentially by the fact that the spectral radius radius of the Dirichlet algebra coincide with the uniform norm in the space of continuous functions, from this comes the fact that one can compute the K-theory of the space as the algebraic K-theory of the Dirichlet algebra. Today, we will not touch the K-theory, the K groups themselves, but only will be interested in the semigroups, of vector bundles.
Sorry, did I understand you correctly? Did you say algebraic K-theory, not the sister algebraic K-theory? Because these are two completely different animals.
Yes, this is a Banach algebra.
Yeah, so you shouldn't say algebraic K-theory because it has a completely different meaning. Algebraic K-theory is equivalent and so on.
Yes, yes.
Okay.
No, it's functional algebraic. And the proof, at least at the level of the semigroup of this identity, comes from this property, which will be used below, by which if we denote by P sister X and PB, P sister A and PB star, the projection in the sister algebra and in the Dirichlet algebra with their norm topologies, then if we pick up a continuous projection, there exists a finite energy projection here, which is homotopic to it, which is a continuous deformation of P in between, in the closest set of projection on sister X. Also, if we pick up two finite energy projection, finite energy because they belongs to B star, no? If we pick up,
Sorry, I'm confused. What's the difference between B and B star? I'm confused.
Where is B?
What is the difference between B and B star?
Sorry. B is the Dirichlet algebra of the initial Dirichlet form on the topological space. B star is the Dirichlet algebra of its stabilization.
Okay. Tomek, I mean, if you have a question, just ask it. I mean, don't force me to each time, let you ask the question. Just do it yourself.
Okay. My question, hello?
Yeah, we can hear you. Yes.
My question, what about K1? Is there a similar approximation result?
By B, one can reconstruct. So the K-theory of B, of the Banach algebra B, is identical to the K-theory, the original K-theory, both for K0 and for K1. Today, since we are concentrated on vector bundles, we will only treat the semigroup which gives rise to K0, like not K1.
Okay, thank you.
And I was saying that two finite energy projections, which are homotopic equivalent in the space of continuous projection, if and only if they are homotopic equivalent in the space of a finite energy projection. So these are the consequences that each connected component of the space of projection on the sister algebra contains one and only one connected components of the space of projection of the sister algebra with in their respective norm topology. In fact, the second one is dense in the first one. So this is essentially the reason by which one can compute, in principle, K0 of the C-star algebra and also of the space X using the projection, the tools of B-star, of the Dirichlet algebra. The proof and all other and many other proofs of this work relies on well-known techniques of K-theory by which if we have a projection P, a continuous projection, this is by regularity can be approximated by an element of the Dirichlet algebra, which does not contain in the spectrum 1/2. And then by Markovianity, taking functions of it, one can approximate it by a projection which has finite energy, a projection in the subalgebra of Dirichlet algebra, in the Dirichlet algebra. These are the techniques we essentially use. So now we come to describe the situation, the setting, the geometric setting we are interested, the one of vector bundles on the space X. Vector bundles means locally trivial and finite dimensional. And vector bundles can be described by projection in the stabilized C-star algebra C-star of X. This is essentially contained in a paper of Swan, coming from also a paper of Serre, which was concerned with algebraic geometry, essentially. So vector bundles can be represented by continuous projection on X with values in the compact operators. In particular, if we consider such a projection, so verifying the identity of a projection, then for any fixed X, the image of P of X is a subspace, is a finite dimensional subspace of the Hilbert space H, and is the fiber of a locally trivial vector bundle. In the opposite direction, if we have a locally trivial vector bundle D, and we pick up a decomposition, a covering, a finite covering, or not finite, but any covering of the space, a partition unit subordinated to the coverings, and a local trivialization for the vector bundle subordinated to the covering, then if we consider this element, so this is a matrix of matrices in which we multiply the function hi by hj. These are the elements of the partition unit, so are positive functions, by the matrix gij, which is the local trivialization, so which is the function matrix that perform the change of Atlas charts.
Sorry, Fabio, I'm a bit confused. So lowercase n is obviously like the dimension of the fiber of your vector bundle. What is capital N?
Capital N is the number of
of elements in this partition of unity. Yes.
Yes.
So I'm using compactness here.
Exactly.
Okay. By the way, I'm also having some hesitation about using here compact operators instead of M infinity. I mean, dense subalgebra here. If you just have a projection compact operators, it's obvious that the image has to be finite dimensional at every point.
But yes, these are continuous projection. So the rank of this projection is locally constant, and since the space is compact, is constant everywhere.
Okay, but anyway, it would suffice to take M infinity instead of compact.
To conclude it,
Thank you.
the second approach. There is another question?
No, I don't see any our question. No, no.
One verifies that this operator P, this function with values in matrices, so in compact operator, verify the equation of a projection or orthogonal projection just by the cocycle property verified by GIJ. Now, using the cocycle property, one verifies this. So this is the connection between vector bundles and projections in this stabilized system algebra. So we see that this stabilization is, even from the, if you want, commutative point of view, of the point of view of a geometer, of geometry, very, very natural to deal with.
Maybe let me quickly add that this last point on your previous slide is beautifully explained in Karoubi's book about K-theory.
This one.
Yeah, the last, no, I mean, this one with local triviality and how you get projection.
Okay.
Yeah, this one, the last point on this slide, that's very nicely done in Karoubi's book.
Well, and also in this with this setting, we have the homotopy equivalence between projection, continuous projection, is equivalent to the Marray von Neumann equivalence of projection in this sense. And isomorphic bundles correspond to equivalent, homotopy equivalent projection. And the equivalent classes of bundles are described by the equivalence classes, homotopy classes of projection. So the space of equivalent classes of vector bundles is just the space of the components, of the connected components of this topological space P C star of X. This is a semigroup with this sum, and by the result above, this semigroup coincide with the space of connected components of the projection of the system of the Dirichlet algebra. So we can use the Dirichlet algebra and the tools of this potential theory to investigate, if we want, vectors, vector bundles on X. And we finally we come to the definition, our definition of energy. The energy of a vector bundle is the infimum of the energy of all possible projection P which represents the bundle. That means all possible projection P by which, point by point, the image of the projection coincides with the fiber of the vector, is isomorphic to the fiber of the vector bundle B. So by construction, this number depends only on V, only through the isomorphism classes. So only on the class of V, only on the class on V in the semigroup of classes of vector bundles. We denote it by vect X.
Sorry,
And
Fabio,
so,
I have some
yes.
questions. I understand that the energy of a trivial bundle will be 0, right?
Yes.
Okay, so this means that it's not only well defined on the isomorphism class, but on stable isomorphism class, right?
Yes. One should.
Okay.
Yes.
But it's defined on K here. Yeah, thank you so much. Yeah.
And so if one has two bundles or two classes of bundles with different energies, that they could not be isomorphic, just by the definition, which is insensitive of the representative. And so if the energy of a vector bundle, or better on its classes, is strictly greater than 0, the vector bundle cannot be trivial. So coming back for just a moment to the point, the main points of classical potential theory we started, we see that the energy of a projection, all in all, is the sum of the energy of these elements Gij, Hi, Hj, where H are the partition of unity, and G are the trivialization. And so we see that the energy of a vector bundle depends on the energy of its representative, of the projection. And this, all in all, depends how smooth.
Sorry, I think that there is a question.
Yes.
Yes, I have a question. If you can hear me.
Yes, I can.
About this stable isomorphism. So your functional is not additive, is subadditive.
Right.
So if you are adding a trivial direct summand, then you can diminish energy.
Typically, yes. In fact, this is one of the next property I will show you.
So this means that if you think about the stable isomorphism class of your vector bundle, it would be a different invariant than the invariant of the isomorphism class.
Yes, but
okay. So I wanted to clarify this point.
Yes.
Okay,
so
thank you.
To finish these slides, I want just to stress that this energy, this number, depends on the energy of these functions. So it depends on how non-constant these functions are, how the partition of unit oscillates, and how the local trivialization Gij are non-constant in some sense. So this is to reconnect this formula, this definition with the original idea we had at the beginning. And in fact, the first property I want to show you is the fact that this energy functional is subadditive on the subgroup, on the semigroup of vector bundles, or isomorphism classes of vector bundles, in the sense that the energy of a sum is in general not greater than the sum of the energies of two summands, V and W. As you noticed, it can be that even if W is trivial, this sum can be trivial, and so on the left-hand side we can have 0. But this is always true. I want to just to illustrate how to prove such subadditivity. This is based on one end on the following lemma, by which if we have a pair PQ of projection, then there exists a pair of finite energy projections which are equivalent to the first pair. So P prime is equivalent to P, Q prime to Q, and they are orthogonal.
Sorry, Fabio, could you please explain one more time what is the relationship between the stabilization of C of X and stabilization of B? And because I'm confused, because one projections are over one C-star algebra, other projections are over another C-star algebra. One more time, what is the relationship between B star and C star of X?
B star is a subspace of C star of X, is in fact the intersection between C star of X and the domain of the stabilized Dirichlet form, of this Dirichlet form.
So B star of X is a subalgebra, right? In B star of
It's
X.
a subalgebra, is the Dirichlet algebra of the stabilization. So in
Okay, thank you so much, Tom.
Subalgebra, yes.
Yeah, thanks.
And
Tomek?
so, yes.
Yes.
No.
Go ahead.
So, not only we can deform, we have the deformation of P and Q in such a way, finite energy deformation, but also the energy of deformed projection are equal to the energy of the initial projection. So P and P prime, Q and Q prime have the same energy. Using these, if we consider two finite energy projection P and Q, and we pick up a corresponding pair P prime and Q prime, which are also orthogonal, then by the very definition of the sum, we have that the energy of the sum of the equivalent classes equals the energy of the equivalent class of the sum of the two orthogonal projection, which is a projection. And using Markovianity, since P prime and Q prime are positive and they are orthogonal in the C star algebra sense, they are also orthogonal in the L2 sense. And so, by the consequence of the Markovianity we illustrated at the beginning, we can write down this inequality. So the energy of the class of this projection sum is less or equal than the sum of the corresponding energy of P prime and Q prime. And so by the lemma above, since P prime and Q prime have the same energies of P and Q, we arrive at the desired inequality, subadditivity property. So you see that to prove subadditivity, Markovianity or a consequence of it is essential. As a second property, one can say that, as already said at the beginning after the definition, one could expect that this number, the energy, could measure the non-triviality of the bundle. We will see that this idea as a concrete realization, at least in low dimension. What does it mean a low dimension in these settings? We say that a Dirichlet form, so a Dirichlet space, if you want, has a low dimension if this inequality holds true. Means that the energy of an element, a function, B, dominates a multiple of the square of the distance between the oscillation. This is essentially the oscillation of the function A, because A bar is, you see, the mean, the arithmetic mean of the supremum and the minimum of the function. So we
may I have a question?
Yes.
In your definition of low dimension, you are using the phrase dimension, low dimension, but it is replaced by some kind of inequality.
Yes.
Is there some estimation of some dimension behind this condition? For instance, in this example, we speak about different kinds of dimensions. For fractals, you can speak about Hausdorff dimension. For this other, you can speak about this Lebesgue dimension.
as you can
the
see,
low
the
dimension in some sense.
this last picture suggests that okay, for Riemannian manifold, we can, this is true by is an elementary inequality coming from integral differential calculus on an interval on a circle, by which the Dirichlet integral on an interval dominates a multiple of the square of the oscillation of a function. But this inequality holds true also in other exotic situations. For example, a bouquet of circles, or also an infinite bouquet of circles, also called the Hawaiian earrings. Also in case of quantum graphs, so one CW compresses, if you want. And also for a large class of the fractals, all the fractals which are PCF in the sense of Kigami and others, for example, the Sierpinski gasket, the famous Sierpinski gasket, this inequality is true. In the case of fractals, many dimensions are associated to a fractal, and the appropriate one are in fact less than 2. There are the walking dimension, the many other dimensions, all of them correspond to a number less than 2. This is why we call the situation in which a Morley type inequality like this holds true, we call these situations low dimensional situation.
Sorry, please correct me if I'm wrong.
Yes.
Did I understand you correctly that any dimensional Riemannian manifold is of low dimension?
No, low dimensional Riemannian manifold are just the one dimensional.
Aha.
This is true only in one dimension, only on the circle for Riemannian manifold. But for other spaces, it can be true. The essential fact is that this inequality implies that the points have strictly positive capacity. And so you can join pieces of spaces on subsets which have positive capacity. And in this case, the positive capacity point is 1 point here, 1 point here, and so on. This is why how this is connected with another aspect of potential theory, with this capacity theory. The nice feature of this Morley inequality is that it's stable, so it persists under stabilization. It means that if this is true at the commutative level on the topological space X, then it's true, appropriately interpreted, appropriately written, is true also for the stabilized Dirichlet form.
But how about higher dimensional manifolds? I don't know, Riemann surfaces, 2 torus, whatever. Does this energy can also measure the non-triviality of a bundle or not? Does this energy?
This is an interesting question, but on one end, this suggests that for higher dimensional manifold, you have to use higher dimensional energies.
Okay.
Not just the 2 energies, no? But you have to use energies with P greater than dimension, typically.
Okay.
This can be done, but that potential theory is nonlinear or non-quadratic. And so there are many, it's not developed. These things are completely new. So this is a one direction one could be interested to investigate.
Okay, thank you very much. Yes, I understand. Yeah.
So all in all, simply by the fact that the stabilization of the Dirichlet forms is very simple, essentially we multiply tens, we take as generator the tensor product of the initial generator, the initial Laplacian L by the identity operator, this Moore inequality is stable, so it's true also for the stabilization. This is not completely surprising in the sense that even if instead of the Moore type inequality, we consider the Poincaré inequality, the spectral gap inequality, since the tensorization is with the identity operator, also the Poincaré inequality is true for the stabilization. No? The spectrum of E star or its associated self-adjoint operator has a gap above 0. But for the purposes of the present setting, to have at the end a non-trivial bound about the energy is the strongest Moore type inequality that should be considered. And now we will see how the result is in fact that if the space, the Dirichlet space has a low dimension, then a vector bundle D, whose energy? Sorry for this
May I
time.
ask a question about this non-commutative inequality? So in this low dimension definition, this A bar was an intermediate value between supremum and infimum. Okay. Now
Yes.
you are taking infimum over all elements of these compact operators.
Yes.
Is there some result, some non-commutative version of the result of an intermediate value behind this result? Is the, okay, let's assume that this infimum is realized at some compact operator. Can this operator be regarded as some kind of
yes.
average?
I don't know. Yes, I don't know this. This is the reason by which I could I can rewrite this oscillation about around the mean of the function. I can rewrite it in this way. No.
Okay.
Where B is a constant function.
Constant operator.
But in the stabilized case, since the elementary system algebra has not an identity, the right way to write it is in this way. I don't know if this is achieved, the infimum is achieved. And I only remember a paper of Christensen collaborators in which investigated the inequalities, this kind of semi-norms, or this kind of norms in the quotient space, connecting them to the idea of a dipole. But in general, I don't know if in fact I don't think this infimum is achievable. But this is a consequence of the first commutative Moore type inequality, and using them, we can prove that if we have a vector bundle whose energy is small enough, then is trivial, because let us pick up a projection which represents the bundle, and suppose that it has energy less than 1/4. I take C equal 1, simplify. Then by the lemma, there exists an element, essentially a compact operator on H, which is close to P. Which is close to P and the distance between these two is dominated by the square root of the energy of P, which by this assumption less than one half. So the distance, the uniform distance in this sister algebra between these two elements is less than one half. But since P is a projection, its spectrum is contained in 0 and 1, in these two point set, and so the spectrum of this P bar is contained in the unit of these two disjoint intervals. They are disjoint because by the assumption delta, this distance, is less than one half. And so one half does not belong to the spectrum of this approximation P bar. Then, if we consider this family of functions, which are 0 if S is less than epsilon, and R1 if epsilon is greater than 1 minus epsilon, then on the spectrum of this P bar, since the spectrum is contained in these two disjoint, the union of these two disjoint interval, then f is a real function and coincide with this square. So we have that computing the function f delta with epsilon equal to delta of P bar, we have a projection. We have essentially a constant projection over x. So, precisely this element of this tensor product can be written in this way by a projection Q, a finite a projection Q of K of H. And then one can estimate the distance, the uniform distance. This is a system, yes, the continuous function. Use uniform distance between the original projection P, representing, I call you representing the vector bundle V, and this projection, constant projection, one can estimate by using the triangle inequality, and then using the calculus in spectral calculus, because pi bar is f0 of pi bar itself. So this distance depends upon the uniform distance between these two functions. But if you compute the distance between f delta and f0, this is exactly equal to delta. And so the sum is strictly less than 1. So we have two elements in a sister algebra at distance less than 1, and then they are homotopically equivalent. So this the original projection P is homotopically equivalent to a constant projection, this one. And this
sorry, Fabio, could you please remind me the meaning of this notation? Here we have these wedges. And what's the meaning of this notation here?
This means the function which has the value 0 when S is less than, this is the maximum and this is the infimum. And so this is the bar is the quotient between them.
Oh.
And so we are the maximum between 0 and this ratio.
Okay.
So
okay. So in other words, just let me write it. So you have like parentheses here.
No, here and here.
Yeah, exactly. So you this is a genuine fraction, but whatever goes into this numerator, denominator is just minimum or maximum, right?
Yes. So it is a function which is constant, equal to 0 on an interval, equal to 1 on another interval, and is linearly interpolated between the two values.
Well, it's a very confusing notation.
No, yes, you have to place the how to say the parentheses here and here.
Oh,
So
so it's really, now I'm
a
completely
fraction
confused.
s minus epsilon over 1 minus 2 epsilon.
Okay, so I press it, I put it here, and I have a certain fraction, right?
Yes, here, exactly.
So what does it mean to have a number, dang number, dang number?
It's a lattice.
No, but this is just a numerical functions which below epsilon is equal to 0. Above 1 minus epsilon is equal to 1. On the right of 1 minus epsilon is equal to 1, and is linear in between, or fine if you want, in between. Is piecewise.
I'm sure there's a much easier way of writing it down than this.
Yes, I could, if I could draw the picture, would be easier. But this function has the property that on the spectrum of this operator, this element p bar, which is contained into this joint interval, the square is real and the square is equal to f, because on these two intervals, the values are or 0 or 1. That's why when we compute these, we get a projection. And at the end, we verified that the original projection P is equivalent, is homotopically equivalent to a constant projection, which represents a trivial vector bundle of the suitable dimension. And so this proves also that the Murray constant mounts below the energy of a non-trivial vector bundle. If the vector bundle is non-trivial, its energy cannot be strictly less than this fraction of the Murray constant. In this sense, we verify that in low dimension, using the Murray inequality, this definition of energy is sensible about the triviality or not of the bundle, of the class of the bundle. The last property we want to stress concerning this subject is the notion of harmonic projection. Why we have a functional on projection, and this the Euler functional derivative, weak derivative of this function will be realized on what we call harmonic projection, and I will show you some of the properties of this projection. For a fixed finite energy projection and the self-adjoint element in the Dirichlet algebra, we have two equivalent properties. P yp is equal to 1 minus p y 1 minus p, and so since they are operators acting on orthogonal spaces, they both have to be 0. This property is equivalent to the representation of this element y as a commutator between a certain element x and the projection P. There is a third. Yes.
In this lemma, Y star must have this upper star. It's a self-adjoint.
This is
What is this?
an upper star. This is the adjoint of Y.
Yeah. Okay. Okay.
The adjoint operator. So it is self-adjoint. Y is self-adjoint. These two properties are both separately equivalent to this third one, which explain the name of tangent vectors. So there exists a smooth C1 path on the real line with values in this Banach algebra, B star, which is a path of projection, of finite energy projection, which start at P is fixed from at the beginning, which start at P, and whose derivative at 0 coincide with Y. So that's this is the reason by which a self-adjoint operator verifying this property or this property will be called a tangent vector at the projection P. These are equivalent ways to think at the tangent vectors, and allows us to define the tangent space of the projection manifold of B star of the Dirichlet algebra at P as the set of self-adjoint elements of the Dirichlet algebra, which verify this, for example, this identity here. This has to be considered as the tangent space to this manifold. Now, if the stabilization would be done with a finite dimensional Hilbert space, so tensorizing with matrices, then B star would be an honest finite dimensional manifold. The complication here is that B star is a Banach space, but is infinite dimensional if the auxiliary Hilbert space is infinite dimensional, as we need to perform all the calculation or the correspondences with the geometric correspondences. So B star, the space of projection in B star is a Banach manifold, which is modeled on B star, on the Banach space B star, is also the quotient of two groups is a homogeneous space, but is infinite dimensional. But for the moment today, we just this is just a definition to pick up to isolate a certain operators in B star, certain elements of B star, which should be, but for this reason, should be thought as the tangent vectors to P. And we have that two properties are equivalent. If we compose the energy, if we can evaluate, if we compute the energy of this family of projection PS for a C1 path starting at P, the result is the derivative as 0 is equal to 0 if and only if the sesquilinear form corresponding to the stabilized Dirichlet forms, sorry, here a star is lost, evaluated between P and Y is equal to 0 for any tangent vector Y. So these tangent vectors form to say the tangent vector of an infinite dimensional manifold, but also allows us to translate this equation in this equation and to speak about harmonic projection. So the critical point of the energy defined on the projection on the star, so those which annihilate this derivation, the critical points are called harmonic projections and are can be identified as those verifying this property in terms of the squilinear form associated to the quadratic form E star. Now, the divergence operator, so the adjoint of the derivation, which represents, which is underlying, the Dirichlet form.
May I have a question?
Yes.
Is this critical point the minimum of the Dirichlet functional?
No, any critical point. Any critical points will be the harmonic projection. If you want, the name comes of course, is suggested by the fact that we are considering the critical points of an energy functional. So we call it harmonics. On the other hand, there is a well-established literature, many efforts, works, in the situation in which people studies maps and harmonic maps between Riemannian manifolds. The critical points of the energy functional of a map between two Riemannian manifolds are called harmonic maps. The difference between with our situation is that B star is a manifold, but a Banach manifold, not a finite dimensional Riemannian manifold. And here I would note, yes.
Fabio, just a reminder that you have -2 minutes left.
-2 minutes.
Yes.
Okay. One can consider the divergence operator, the Laplacian, is better for these purposes to understand it, for example, the Laplacian between B and the dual of B star, sorry, B star and the dual of B star, and verifies that a projection P is harmonic if and only if satisfies this equation. See, it commutes with the operator obtaining, applying to P itself the Laplacian, the generalized Laplacian. And also, this equation is equivalent to this equation where U is the orthogonal symmetry corresponding to P. The orthogonal symmetry with respect to the image of P, which is a generalization of the eigenvalue of the eigenvector equation for the usual Laplacian. And the only example I can show you is that on the sphere, if one considers the Bott bundle, which is described, represented by this 2 by 2 matrix of continuous function on the sphere, then this equation is verified, is in fact verified, and in this particular case, gamma, this gamma, which is defined in this way, the Carré-Duchamp, is a multiple of the trace. These are functionals, right? And is a multiple of the trace on C star of X. We don't know if the Bott bundle, if this projection is harmonic, of course, but we don't know if is the projection minimizing the energy of the Bott bundle, which is a non-trivial bundle on the sphere. And this essentially concludes the seminar.
Ok, thank you very much. Grazie mille.
Grazie a voi.
Piacere. Okay, guys, any other questions? Adam.
I don't know whether it is a suitable question, but the name energy suggests some physical interpretation of this stuff. So I wonder whether this has something to do with, you know, minimizing this energy functional in maybe some connection with quantum field theory. I don't know. I'm just thinking loudly.
But one can imagine to apply these results, this reason, this setting to the bundles on the two torus, which one can build in the from the Hamiltonian of the quantum Hall effects by considering the first eigenvalue, for example. No, there the spectrum is a band spectrum, is a continuous spectrum. But in certain situation, approximating situation, even for each fiber indexed by a point in the two torus by periodicity, in each fiber the spectrum is discrete. And then if we consider the first eigenvalue, non-trivial eigenvalue of all of these fibered Hamiltonians, you build up a a bundle, a locally trivial bundle, which is clearly connected with the energy of the system, at least in that region of the spectrum. This is would be a natural setting in which the name energy could really mean energy of a system, of a quantum system.
The quantum Hall effect, yes?
Yes.
Ok, thank you.
Ok, c'è ancora una domanda. Richard, Santiago, are you guys good?
I have a very silly question, to be
Go
honest.
ahead, Santiago.
Okay, so similar to the context you just mentioned, perhaps, well, what if you're interested in dealing with the Dirac equation with a wave function which is spin-order valued? Then those spinors can be thought of in a way as vectors, right? So you could define a fiber bundle with these wave functions and then perhaps minimizing the energy in some way. Well, it could maybe like here you showed that low energy is like closer to triviality, right? So maybe like a trivial spinor bundle here would be sort of like a base state of the system, like a lowest energy eigenstate, something like that.
Yes. No, I was thinking to the Dirac equation in quantum theory. No, but if you consider the Dirac operator on a Riemannian manifold,
Uh-huh.
So in that case, there is a result we got with Jean-Luc that the Dirac Laplacian, so the square of the Dirac operator on a Riemannian manifold, gives rise to a Dirichlet form if and only if the curvature operator is non-negative.
Okay.
So the Buchner or connection Laplacian is always a Dirichlet form on the Clifford bundle, of course, on the Clifford algebra of a manifold. So on the section of the Clifford bundle, but the Dirac Laplacian itself has a quadratic form which is a Dirichlet form in a non-commutative sense if and only if the curvature operator is non-negative. In that setting, you can apply this, of course, and you are right. Would be interesting to investigate if this approach, these tools could provide could provide a connection with the triviality of spinor bundles.
Right.
So, in particular, which was a very interesting situation, of course.
Mm-hmm. Yeah, actually, well, there was a very I don't know if it's sort of famous or not, but at least in spectral geometry, sort of an annoying problem that has been on many people's sides for a long time, which is isoparometric inequality by Professor Benguria here at Universidad Católica in Chile. And well, basically, there's all sorts of different connections in the. This wasn't actually the problem I wanted to talk about. This sort of a Rayleigh-Faber-Cran type inequality for that has been conjectured for a Dirac operator instead of the classical Laplacian. The thing is, people don't really know how to optimize over spinors. So an approach like this would be an interesting approach, to try to minimize an energy, which in the case of the Laplacian is really easy to do because your wave functions are scalar valued. But here with spinors, like these techniques that I use that are the symmetric rearrangements and this sort of stuff, well, it doesn't work, and the functionals that you have to define an energy are not really very obvious for these geometric problems. I mean, this is in spectral geometry, but I mean, yeah, this is only motivation for my question. You already answered, and I'm very satisfied. So thank you.
Okay, great. So Santiago is happy. Anybody else? Richard?
I'm happy.
Okay, that's so
May I
nice.
have a question?
Yes.
About the last point of your talk, existence of harmonic projection minimizing energy. When I was asking you about positive definiteness of this Dirichlet form, I was interested in uniqueness of this minimum of this functional, which is harmonic in your sense. But you said that there could be some critical points which are not related to this minimum. So my question is this Dirichlet functional a Morse function on this manifold, infinite dimensional manifold of projections?
This is a very nice subject to investigate, but you notice that this last part concerning harmonic projections, I avoid to talk about existence, because existence, even between two manifolds, the existence not of critical points, but the existence of the projection minimizing energy is a very, very difficult problem. And there are very interesting and complicated phenomena by which on spheres, on very common situation, the energy of maps, minimizing the energy of maps between two spheres, one can get zero. Are phenomena that are related to topology, very strong to the topology of the two manifolds. here we have the extra complication or that the target manifold is infinite dimensional, and we have no tools by far no tools to try to prove the existence of minima, of minimizing projection at all. It would be already very interesting that in case of circle, spheres, torus, to get to prove that in some equivalent classes, homotopy class of projection, there exists a minimizing one, an energy minimizing projection. Even in this, for cases of when X is a torus or is a sphere, is a two-sphere, for example, this will be very interesting, but we don't have idea how to approach the problem, which is reasonably very hard.
Yeah, now we can hear you.
Okay,
Yes.
so I was not asking about mappings, harmonic mappings between manifolds. I was asking about the Dirichlet functional as a function on the space of these projections. And then
Yes.
I was asking about whether this function has the Morse property. I understand that minimizing property.
I told you, this is interesting, but we
difficult problem.
didn't try to follow this, which of course would be, of course, interesting.
So this is not known.
All the
This
works
Morse
of
property?
both about these functional, the energy functions in gauge theory. One could have those works as a guide, for example.
Mm-hmm. So this means that some of these critical points could be highly degenerate.
But yes.
Okay. Thank you.
The only other example I could communicate to you is the one of the circle, in which if you take the Mobius band, the Mobius vector bundle on a circle, this is non-trivial in real K theory, and one can verify that a projection representing it is critical, and also all other powers of the Mobius band, of the Mobius vector bundle, all of them are critical projection. In that case, as in the case of the sphere, this Carré-Duchamp, so is essentially the square of the gradient, the square of the derivation, is a multiple of the identity, or better, is the multiple of the trace. So is a constant multiple of the trace. And this eigenvector equation looks like the usual one for the eigenvector of functions on a sphere or on a manifold. We don't know if this fact, which is true in on 1 and 2 dimensional spheres, is a general feature. The fact that the distribution of the energy of the orthogonal symmetry of harmonic projection P verifies is a multiple, a scalar multiple of the trace. We don't know. We verified in these situations, but we don't know if there is some general explanation for this.
Okay. Since there are no other questions or comments, let me ask my general question. You see, a reason why your talk is very interesting to me is because I would like to have a similar kind of an invariant, but for principal bundles, not vector bundles. And there is something which measures very non-triviality, okay? So as long as you're, but here the difficulty is precisely in the setting of principal bundles that are not locally trivial. When we have a locally trivial principal bundle, I'm talking everything is compact for me, okay? All my algebras are unital, just to focus attention. So as long as you have any locally trivial compact Hausdorff principal bundle, then there is the concept of a local triviality dimension. And this is precisely what measures how far away your principal bundle is from being trivial. This is a very nice invariant, and in fact we are very much interested in the following result, which stems from the celebrated Bosso-Guram theorem, notably that you cannot have a continuous equivariant map from a bundle which is less trivial to a bundle which is more non-trivial. Okay, so somehow when you are G equivariant, where G is your group, and continuous, then there is a no-go theorem, right? A very simple incarnation is in Bosso-Gulam, where you just have Z2 as your group and S2 as your space, and so on and so forth. So, but there is a very serious problem which is directly related to a very famous Hilbert-Smith problem, which is very, very difficult, more or less like a millennium problem. And this is the question. We would like to have the same no-go theorem when we go between certain constructions of principal bundles that are not locally trivial. So, okay, to cut a long story short, would you be able, for starters, to construct a similar energy invariant for principal bundles, for instance, for the frame bundles of your vector bundles?
No, I confess to you that we didn't even thought about this.
Okay, okay.
I just express that my positive mood in this direction, if you want, but I couldn't. Would be a matter of a night discussion.
Okay, okay. Okay, okay. So in this case, let us thank Fabio again for his very interesting talk. Grazie.
Thanks all of you.
I stop recording.